Now instruction fetch and data and control path basically. Let's look at that area. So let's say I have a instruction memory. Okay, so by the instruction memory I mean the part of the memory at which I'm storing all the instruction. Later we'll see we can actually divide memory into two physical component. One contains only instruction memory, other contains data memory, and in that case we call them as cache memories. But right now let's not go into that complicacy. Just think I have a memory component which stores my instruction. That's what I call it as an instruction memory. Okay. So this instruction memory stores your machine code of the program serially from one address to another. So we have this address, like address of that instruction, the instruction memory address to be read in, that comes from your PC, right? Program counter, by definition, it holds the address from which you need to access the next instruction. So your PC is supplying your address to the instruction memory, and then the data coming out of the instruction memory is your instruction code, right? Machine code. So that goes into your instruction register. And then once the fetch is done, PC need to get ready for fetching the next instruction, which is usually PC plus one. Like we are talking about the sequential programming here. So one instruction is done, next instruction recites exactly one address above. So here is one more assumption. Why it is 1? Because we are assuming this memory is word addressable memory. So each address contains one single word. But if you recall, the MIPS, for example, assumes a byte addressable memory. So from one instruction to another, the address gap is 4. So that's when we need to add a 4 instead of 1 if I assume a byte addressable memory. Okay, so if you remember this for all the address calculation around the MIPS and stuff like that, especially with the jump and BNE, like branch on not equal, branch on equal, that kind of instructions, machine code determination, the branch offset, we all assumed PC plus 4 as a next instruction address, right? So it was done like this, like instead of 1, just add a 4 there. But for our class, our assumption is our memory is word addressable, so that's why we will bump up PC by 1 address. Okay, so from startup address, you will have one more to point to the next instruction. So we deploy an addition circuit there. My current PC plus 1 is going back to the PC register. So these are the components, right? Now the control signal here, we can well determine PC and instruction, these two register are registered. It has a load signal. Of course, it has a clock, reset, etc. Those are common thing. We're just not focusing on that right now. Its important signal is a load. Okay, load for the instruction, load for the PC, and instruction memory. It has a read and write. Instruction memory during the execution, it is read only mode. So controller will need to produce a 1 and 0 at the appropriate time, right? When the instruction fetch is done, it need to make sure read is 1, write is 0. Otherwise, just keep it 0, 0. And then at various phases, we need to turn on the load signal. Controller will control that. So that's the control path for the instruction fetch. Now let's talk about R-type instruction, data and control path. Okay. So as I said, data path designing is like you consider each instructions and make a data path for each individual instruction. However, one catch is there, like if the instructions are very alike, like for example, your subtraction, multiplication and addition, these operations and logic operations, those are kind of very similar operations. So For the common operation, if the data flow path is kind of common, then we are okay. We are okay to have kind of look at the group of instruction as it is. Okay, so you will probably understand what I mean by that in few minutes. So R type, what we have, right? Your operation is a destination register equal to some source register and operating and some operation like an addition, subtraction, multiplication, or and, nor, or those kind of operation with the register RT, right? And this is your format for the R type instruction. So what for this type of operations, what we all need is to involve ALU with some operation code. Its source of two operands being from the register file, right? R1 and R2. Let's say RS and RT are coming from as an R1 and R2, and ALU result is stored back into the register file as an RD. So from the format, we know these bits from 21 to 25 is designated for RS register code or RS register value, right? 0 to 31, whatever the RS register we put there. RT is a value of the like RT register supplied in your machine code, and RD is a register that is when supplied in the machine code. So we draw bit 11, 15 as a RD destination register, connect it to the right address, that 5 bit. So we picking up 5 bit. So our instruction is 32 bit, which is coming from the instruction register. Later we'll just assume it is coming from the instruction memory directly. We don't have an instruction register. There can be various little difference in the circuits, but that's not important. Importance is that we are having the instruction encoded, and from there I am connecting directly those logic path, an electrical signal from the 32 bit. RS, the 5 bit is coming from bit 21 to 25. Those 5 signals are connected to the R1 address. So RS will appear as a R1 data after the read is done. And RT is connected, this bit 16 to 20 is connected to the R2 address as an RT, and RD 11 to 15, as I've told, is connected to the right address because I need to write back to the RD register. And the source of the data, write data, is coming as an output of the ALU because operation is done, ALU created the result, that result I need to write back to the register file. And source operand coming from R1 and R2 data. So this is general R type instruction data path. Now we have one special operation called shift amount, right? So this is general. Shift amount data, like shift operation data path is something like this. One of the operand RS coming from your register, but the other operand, the shift amount, this 5 bit, 6 to 10, that is coming from the encoded machine code itself, like bit 6 to 10. So that 5 bit for the shift instruction, I'm connecting the RS into the R1 register, RD destination, of course, this 11 to 15 to the right address. ALU output is basically a source of the right data for the register file. But the second operand for the ALU for the shift operation is coming from the bit 6 to 10 of the instruction itself. So I'm connecting that 5 bit directly to the operation. There is, of course, one little thing we need to take care of. This operand is input port is 32 bit and shift amount is 5 bit. So we need to actually pad the input of the operand 2 in the ALU with 27 zeros. That's easy. Basically, you just ground those 27 bits for this operation, right? So that's the shift data path. And then we have another, like JR, jump register. That's also your register, like R type instruction, where your jump register is PC equals RS by the definition of instruction set architecture in the lecture 1 that we have done. Your RS is encoded in 21 to 25. Rest of the register I don't care. You put zeros there in the code. It doesn't matter. So data path, that means I need to read from register RS, which is connected to the R1 address. Okay. And then the read, output read is connected to the PC. So your PC is practically is getting an address from the register which is stored in the register file. So that's the data path for the JR or jump register instruction data path. Now we have these 4 different things, right? So far, instruction fetch data path, R type general instruction, shift, and jump register. Now we need to combine them, these 3 data path together to make an R type data path, R type instruction data path. So we start with your instruction fetch circuit, okay, instruction memory, PC, plus 1, etc. Then we need to support these 3 type of operations there. That is number 1, which is like RD equals RS, some operation with RT. Then we have shift. Okay, so we are kind of superposing one data path on top of another with this common components, right? We are superposing on top of another. Next data path is your PC equals RS, which is this. Now see, we have 2 data source conflict potentially. One is for the shift amount, which is conflicting with the normal other arithmetic and logical operation where the operand is coming directly from the R2 output, but for the shift it is coming from the instruction encoding itself. So we have one data conflict, and other data conflict is your PC, source of the PC either is coming from your adder PC plus 1 or from the R1 register output. Okay, those two we basically just apply multiplexer. So remember, I have told you the multiplexer is very important component. It is used kind of everywhere in the processor. Wherever there is this data source conflict, we just resolved it using multiplexer. So we place multiplexer there, and then we have the complete control signal list, right? So we have PC load, memory read and write. Here, see, there is, I have kind of removed the instruction register from this case because I'm assuming instruction memory read only, and it will supply the instruction throughout. Okay, so this is just assumption for this slide and this part of the lecture, just to keep the circuit simpler, little bit simpler. All right, so we have memory read and write is for the instruction memory. We have register read and write for the, as a control from the register file. We have operation code for the ALU operation. Okay, now we have 2 multiplexer selection, address selection, let's call it address selection 1 and ALU selection 1. Okay, these 2. So this will, depending on the operation code, it will go and either select from the shift amount or select from the register 2 R2 output port. Okay, and this address selection mask will either select PC plus 1 or it will select from this R1 output, data output, depending on whether I am doing an JR operation or not. So our controller need to actually go and set these signals during the different cycles, like these 5 cycles, appropriately. All right, but this is my control path for the R instruction.